last class we started with selective harmonic elimination. So, this is another form of pulse width modulation, wherein we are introducing the notches to the pole voltages such that it has the half wave symmetry as well as the quarter wave symmetry, same like in the case of a sine triangle PWM. And the notches are introduced with a purpose, so that low frequency harmonics, let us take 5th, 7th, maybe 11th, 13th, the harmonics can be eliminated. At the same time, the fundamental amplitude can be controlled depending on the frequency. So, if you see the figure here, the two waveforms are given. The first waveform here, we are introducing the notches at alpha 1 and alpha 2. Okay. Now, the second waveform, we are introducing more notches. Okay. So, if you see the from the pi by 2 period, we have the quarter wave symmetry. At the same time, the half wave symmetry we have, we can see here, this negative half is equal to the positive half. Okay. Now, we have to decide what should be the width of alpha 1, alpha 2, or angle at which alpha 1, alpha should be introduced such that the pole voltage switches between the positive plus VDC by 2 and the minus VDC by 2. So, let us do the Fourier series for the general for a general PWM with a general notch. So, the harmonic analysis, if you see Fourier series, it will be, that is Vn. Vn is equal to, it can be written 2 into VDC, our DC link voltage, divided by n pi. Okay. You want to see the RMS value. So, you have to divide by root 2 into 2 cos n alpha 1 minus cos n alpha 2 plus cos n alpha 3, this way it goes, finally will be minus 1. Okay. This how do you get it? This we are getting from the Fourier series expression. So, Fourier series expression we can write it like this, V n, I am just repeating, the RMS value is equal to 1 by root 2 4 by pi VDC by 2. So, this is the integration 0 to alpha 1 sin n theta d theta, then minus alpha 1 to alpha 2 sin n theta d theta plus alpha 2 to alpha 3. See, here is a general thing. So, depending on the notch, here in that case 0 to alpha 1, here you have the alpha 1 is, this is in the negative. So, you have to negative, you have to introduce here, but here alpha to alpha, alpha 1 to alpha 2 is positive. So, depending on the notch, you have to introduce the positive negative sign, but this is the general expression sin n theta d theta. So, this way it goes. Finally, you will get alpha p to pi by 2. That is why this 1 comes here, this one alpha p to sin n theta d theta. So, this is a general expression. So, for your notch width, accordingly you have to write the thing. 0 to alpha 1 is positive, alpha 1 to alpha 2 is negative. then alpha 2, alpha 3. Here it is alpha 2, alpha 3. So, this way it goes. So, when you expand everything, you will get this 2 times you will get it, because alpha 1 is coming here, alpha 2 is coming here, alpha 3 is coming here, and next side also it will come here. So, 2 times that will come. Okay. From this one, let us write down the equation for harmonics 1, harmonics 5th, harmonic 7th. That means the harmonics order of fundamental, 5th, 7th, 11th and 13th. How the equation happens. So, let us go to the next page now. See, let us start with the fundamental. So, fundamental will be V1 is equal to 0.45. You can expand the previous waveform into 2 cos alpha 1 minus alpha 2 plus cos alpha 3 minus cos alpha 4 minus 1. This is the fundamental equation. So, if you see, we want to control 11th, we want to control, if you see here, fundamental, 5th, 11th, 5th, 7th, 11th and 13th. So, if you see here, the angles required, we require how many equations? 5 equations are required to control. So, correspondingly, we require starting from 0, then alpha 1, alpha 2, alpha 3, alpha 4, 5 angles starting from 0 is required. Now, let us take the 5th harmonic. 5th harmonics will be, we want the 5th harmonics to be 0. So, I will put it 0. So, the equation will be cos 5 alpha 1 minus cos 5 alpha 2 plus cos 5 alpha 3 minus cos 5 alpha 4, okay, minus 0.5. This is the equation. This is for the 5th harmonic. Now, let us take for the 7th harmonics. So, n we have to replace, instead of 5 we have to replace 7. So, this will be in the original previous equation, if you do it, this will be cos 7 alpha 1 minus cos 7 alpha 2 plus cos 7 alpha 3 minus cos 7 alpha 4 minus 0.5. This is 11th. Let us take the 13th harmonics. No, sorry, 11th harmonic. That also we want 0. So, we want all the lower harmonics from 5 to 13 to be 0. Then this will be cos 11 alpha 1 minus cos 11 alpha 2 plus cos 11 alpha 3 minus cos 11 alpha 4 minus 0.5. Same way, we can also write the 13th harmonic. That also we want to be 0. So, it will be cos 13 alpha 1 minus cos 13 alpha 2 plus cos 13 alpha 3 minus cos 13 alpha 4 minus 0.5. So, if you see here, we have 5 equations, okay, and we have 1, 2, 3, 4 unknowns to be find out. Based from these 5 equations, we have to find out what is alpha 1, alpha 2, alpha 3, alpha 4, such that V1 is our required value and this harmonics are 0. So, if the V1 is fixed, let us take for a output frequency is fixed, then V1 the required RMS we can put it and we can solve this one. Now take a case where a general variable speed operation. Let's take a we are using the harmonic elimination for a 3-phase motor control application where the frequency varies from 0 to 50 hertz. Let us take the frequency resolution. We are in a step of increasing the speed 1 hertz. So 50 times we have to calculate the alpha 1, alpha 2, alpha 3, alpha 4 and V1, because for different speed of operation as the motor increases, the fundamental amplitude varies in proportion to the speed. So 0 to 50, if you are increasing the speed in one step in 1 hertz, that means 50 steps are required. 50 times we have to solve this one because the V1 is varying, and we have to compute alpha 1, alpha 2, alpha 3, then we have to store this pattern in a memory and output. So in some cases, suppose we want to eliminate the next harmonics also, that is the 17th and 19th, then number of equations will be more. So this will increase the computation, it requires lot of offline computation storing. But what we want in a control, quickly online correction, that is the best way. So that is not possible here. So even though selective harmonic elimination is available in literature, it is seldom used in motor drives application just because of extensive offline computation. Okay. But in multi-level, in the context of multi-level inverters, still these harmonic elimination schemes, people are coming with PWM techniques. Okay, but we will not coming to that one now. So only what we want to remember here, to suppress the low order harmonics, we have to introduce the notches with the proper symmetry, then write down the Fourier series, and what are the harmonics to eliminate it, along with the required fundamental, we have to write this equation and solve it. Okay. Here, as I told before, for 3-phase application, the sine triangle PWM is the best approach, wherein we have the fixed triangle frequency and whatever the amplitude fundamental, that is the V1 what we require. Okay. And with that frequency, we generate the corresponding sinusoidal waveform with 120 degree phase shift and do the appropriate switching. So whenever we want to vary V1, just vary the modulating wave, corresponding modulated wave amplitude. So automatically the fundamental is generated. At the same time, harmonics are shifted to the high frequency side, which is proportional to our FC. So again, for 3-phase case, let us go to the next page, how the harmonic elimination for the 3-phase case. Let us draw the triangle wave. So let us take the corresponding modulating wave. This is the modulating wave for A phase. Okay. Now B phase will be 120 degree phase shifted. So let us go with a different color. This is the B phase. Then C phase will be this amplitude of ABC phase, even though it are 120 degree, amplitude are the same. That depends on the for variable speed operation or what is the fundamental we require. Okay. Now this is the C phase. Okay. Now this we will be comparing with a fixed triangle frequency. So triangle frequency will be high frequency triangle waveform. See here for motor drive applications, this is called the VC carrier, this is called the carrier wave and these are the VMT. So 3 phases. So for the inverter we have the 3 legs like this. you have the VDC and 3 loads like this. Okay. Let us say that if it is for the motor, it is motor. So, for the ABC phases, depending on when the triangle is greater than the sine wave, top switch is on. That when the triangle is less than the triangle, we will be using this one. So, the same sequence, if you say, it will go 1 3 5. Now, here this is the bottom one. So, if you see the previous that sequencing, it is numbering is like this. Okay. So, when the corresponding, when the A phase sine is greater than the triangle, top is on. Sine less than the triangle, the bottom switch is on. So, this independently we carry for the 3 phases A, B, C. Okay. Now, how to choose the triangle waveform? For motor drive applications, we want the PWM waveform have the same symmetry like the sine wave. We should have the quarter wave symmetry. When you fold it, it should exactly match, and the negative half should be equal to the positive half. So, we will always use FC is an odd multiple of FC is an odd multiple of FM, our modulating waveform. So, that will, and let us take 21 times, that is a high frequency, you can say 21 times. And also we will use, it is 3 times, FC is proportional to 3 times FM, 3 times. What is the advantage? For motor drive applications, if you see here, as I told in the previous class, we are connecting like this. The neutral is not connected anywhere. So, in the PWM waveform, VAN, VBN, if the triplen voltage is there, triplen current will not flow because the neutral is removed. So, if you use 3 times the fundamental and odd multiple and 3 times the fundamental, this carrier frequency at FC is it 3 FC, and its sidebands will be completely the currents in the phase will be completely suppressed. This is one way of suppressing the effect of low order harmonics. Because the neutral is removed, the harmonics, the current harmonics at 3 times FC, that is third harmonic, FC and sidebands will not be there. So, the next higher harmonics will be at the sidebands of 2 FC and its sidebands. Okay. Now, this way we can use it, sine triangle PWM. Now, the purpose of the PWM is to have a nearly, so even though we are controlling the voltage, what we require is nearly sinusoidal current. We require nearly sinusoidal current. So, with the switching, the current will be, with the ripple current will be, it is following like this. So, the current is nearly sinusoidal and the harmonics are shifted to high frequency side. But sine triangle PWM, we require a triangle waveform and a sine wave we have to generate, it can be generated. And for very high frequencies of operation, FC is very high, the synchronization, that is a zero crossing of the triangle and the sine need not, we do not have to worry. But for motor drive applications, let us see, for motor drive applications, high frequency PWM is preferred. High frequency PWM is not preferred. So, So, this will lead to low frequency FC carrier, FC. But low frequency SE means the sideband, it may boost the low order harmonics. Okay. So, these are the problem. Also, the sine triangle PWM synchronization is required, that is exact zero crossing should be matching, that we will not be talking about it now. But the whole purpose of PWM, the whole purpose of the PWM is to have the purpose of PWM operation is to have a nearly sinusoidal current. Sinusoidal current. Why? So, sinusoidal current will get constant torque, ripple torque will not be there, harmonics losses will be there, efficiency is more. Then another PWM scheme is called, is very popular. This is called current hysteresis type control. This is used in high dynamics performance applications and it is very easy to implement. So, we will talk about current hysteresis controller now. Current hysteresis controlled PWM. So, in current hysteresis controlled PWM, we want nearly sinusoidal current. That means to generate sinusoidal current over the output current waveform, it is used in motor drive applications. So, we use PWM so that the current ripple is confined to a hysteresis band, so that the average variation of the current is nearly sinusoidal. Okay, this is the thing. So, we switch such that we will introduce envelope along this reference current such that the current is, that means we are introducing a envelope. So, we will mark with a different thing. We are introducing an envelope here. This is called the hysteresis band. Such that the current ripple is not allowed to go above or below this band. So, current is always current. The current ripple in hysteresis controller, the current ripple is confined within a hysteresis band. Okay. Now, what are the things we require? How to design? One, how to determine the hysteresis band. This is very important. So that, why? See, now we don't know what is the switching frequency. Previously, for sine triangle PWM, the switching frequency was FC for sine triangle. The PWM frequency is FC. Here we don't know what is the switching frequency. This is very important. So, depend on the devices and switching losses, the switching frequency should be controlled. That means the switching frequency depends on the devices. Then what is the switching frequency? PWM, switching frequency, that we don't know. So this is dependent on the hysteresis band. So we have to design our hysteresis band, these are related, depend on the hysteresis band, so that the switching frequency is controlled. Okay. Now type of, this also depends on the type of load, load with inductive or load with back EMF load. So let us design, how to design the hysteresis band for a particular switching frequency, right? And what are the merits and demerits of current hysteresis controller. This we will study now. So let us take our basic inverter schematic, that is our half bridge configuration, and let us define a, see, hysteresis boundary, now we are going to for a general boundary. This is a sinusoidal reference current and a boundary along the sinusoidal reference. We can also have a DC current and we can design a boundary here, so that the ripple is within this one. Okay. So that is also possible. So let us take a general case for a half bridge converter. Let us draw our basic single phase, the basic inverter configuration. This is VDC by 2, this is also VDC by 2. Let us take a load with the back EMF, that is EC, and let us take a DC motor. This is S1, this is S2. It has the freewheeling diode also there, so it is bidirectional switch. Okay. Now let us say we want a current, that is the IL, a DC. So current has to be controlled depending on the DC, depending on the load. So this is the current we want, and we will introduce the hysteresis band, so that the current is controlled with the ripple is controlled within this band. So let us say we will enlarge for analysis. Let us say this is the band. So this is the IP, this is the IV, upper band and lower band. Okay. Now let us say the switching sequence. When we know when the S1 is on, current will flow through IL. So IL will keep on increase. The moment it touches the IP, we are turning off S1 and turning on S2. The turning on S2 means what will happen? This VDC, lower VDC by 2 and the back EMF will oppose this current. So the current will slowly decrease. So current will slowly decrease, load current. Again moment it comes here, again we are turning on. So it will go like this. So this way it will go like this. So the rising slope and the falling slope need not be equal. So falling slope will be here faster because of the EC is opposing. EC plus VDC by 2 both are opposing. So this is the current ripple. Let us see what is the switching sequence based on this one. So when the positive slope, we are turning on S1, S1 on. This is S1 on. During the negative slope, that is VDC by 2. Okay. We are seeing the voltage VA0, this is VA0. When the S2 is on, during this period, it is minus VDC by 2. So this way we are switching. This also a PWM operation. Pulse width is controlled. Okay. here depending on the current hysteresis band. Now, let us see for a hysteresis band IP and IV, what is the turn on and turn off period. If you know the turn on and turn off period, we can find out the switching frequency. The period is T on plus T off, that is one period, that is this is the T period. So, T is known, we can find out the switching frequency. Let us take when S1 is on, S1 on, the di by dt, d IL by dt is equal to VDC by 2 minus EC divided by L. So, if you see here, this is opposing, plus is here minus. So, VDC by 2 minus L by L. Now, from this one, this is also equal to, what is DIL? DIL is equal to IP minus IV. IP minus IV divided by T on, S1 on, T on. Okay. What is IP minus IV? That is delta I. So, IP minus IV is equal to delta I is equal to IP minus IV. Okay. So, this is equal to delta I by T O. Okay. So, from this one we can find out T on. How do you find out T on? From this equation. T on is equal to, from this equation, T on is equal to IP minus IV, that is delta I divided by VDC by 2 minus EC. Okay. So, EC is the back EMF of the machine. So, the PWM period is, assuming it is so high, during this period EC is not varying, EC is constant. So, that is we are representing EC. So, we can find out T on here. Now, let us take the T off period. T on we have found out. So, let us go to the T off period. So, T on we can again, T on we can write here, this is delta I by VDC by 2 minus EC. Okay. So, now let us write the T off period. What happened during the T off? Now, let us take the T off period. So, T off period, again the slope is equal to delta I divided by T off. So, T, this is, if you see here, this is T on and this is T off. So, delta I divided by T off, that is a slope. Delta I by divided by T off is equal to now it is VDC by 2 plus EC. So, here the slope is negative, but we are not taking the negative into consideration because we only want the T off period. So, we are taking the absolute value VDC by 2 plus EC divided by L. So, L into di by dt of, that is the voltage across the inductance is equal to VDC by 2 EC. When this is turned on, this whole voltage has to drop across this one. Now, from this one we can find out T off is equal to what? T of is equal to L into here also see that delta I by T1 is equal to, you have to multiply it by L is also there, that is missing here. This L has to be here, this L has to go here. Okay. So, this is also whole multiplied by L, L has to be here. So, here also L into delta I divided by VDC by 2 plus EC. So, we got the T off and T on. Now, we know the period T. What is T off? T is equal to, period is equal to T on plus T off. Okay. So, let us go to the next page now. So, T, the total period T is equal to T on plus T off is equal to L into delta I by VDC by 2 minus EC plus L into delta I by VDC by 2 plus EC. Okay. This can also be written as L into delta I into 1 by VDC by 2 minus EC plus 1 by VDC by 2 plus E. So, this is, so we can reduce, this is A plus B into A minus B. So, this also we can write as VDC by 2 whole square minus EC square. Here let us, so here it will be this A plus B into A minus B. So, here it will be VDC by 2 plus EC, here it will be VDC by 2 minus EC, that is from this one. So, EC and EC will go, the final equation will be 2 into VDC by 2 divided by VDC by 2 whole square minus EC square. This is equal to our T. Okay. We got T. Once T is known, we can find out the switching frequency. That is our PWM frequency. So, what is the PWM frequency here? PWM frequency is equal to 1 by T equal to our F. Okay, here we have to put the LDI. LDI we have missed here. So, LDI is also there. L delta I, that is also there. So, F is equal to what? Inverse of this one. FEC is equal to inverse of this one, that is VDC by 2 whole square minus EC square divided by 2 into VDC by 2 into L into delta I. So, what is the purpose of deriving this equation? See, I have brought the hysteresis band, that is delta I, into this one, and the frequency PWM switching frequency related to the PWM switching frequency phi. So, this equation shows For a particular delta I, for inverter, VDC by 2, the DC link is fixed. Assume for a DC motor, if EC is fixed, then the frequency is related to delta I. Okay. So, what is the relation? Again, this we can again rewrite in different form like this. Now, delta I is equal to, we will write it in a different color, delta I is equal to what? VDC by 2 whole square minus EC square divided by, see 2 goes, it divided by VDC L F. So, this is the relation delta I and F. So, if you see, if you want high frequency PWM, that means F is more. High frequency we require delta I will be very small. So, for frequency to be reduced, we do not want high frequency PWM, then the delta I will increase. The moment delta I increase means current ripple amplitude will increase. So, there should be a compromise. So, from this one, for a fixed DC and a fixed basis band and for a fixed switching frequency, delta I can be found out. Okay. With a fixed tolerance band Fi, the switching frequency F depends on the output voltage required. Now, let us take EC. EC is varying. Let us take, this is our for the 3-phase motor operation, this is that EC is the single phase voltage, that is the back EMF voltage from one phase. So, EC will be varying sinusoidally, back EMF wave. Then what happened to the frequency? So, this is for switching frequency. Now, for variable frequency, motor drive application, if we can derive for one phase, we can derive for the other phase also. Let us write. So, with a fixed tolerance band, with a fixed tolerance band delta I, the switching frequency F depends on the output voltage, load voltage, output voltage. Here we have represented in our figure as AC, output voltage AC. Now, let us take EC is varying sinusoidally, that means for a 3-phase operation where the single phase voltages vary sinusoidally, what ABC it varies with a 120 degree difference. So, let us take a for a sinusoidally varying, if EC is equal to some E maximum into sin omega t. See, we are from the DC motor, that is we made from the simple analysis, that is EC is fixed. We found out how the delta I and F is varied. Now, EC we make it a variable, that is sinusoidally varying signal. That way we are slowly introduce the hysteresis band required for motor drive application. Then what happens? The inverter switching frequency here, if EC, then F, the switching frequency varies for a fixed hysteresis band. With a fixed hysteresis band delta I. Okay. So, let us go back to the previous equation. F is equal to VDC by 2 whole square divided by EC square divided by VDC into L delta I. So, let us take when EC is equal to 0. EC is equal to 0, then F is equal to F maximum, that is the maximum switching frequency, is equal to how much it will come, is equal to Fm is equal to VDC, we can square it, EC is equal to 0, this will be become VDC by 4 divided by L delta I. This is the Fm. So, this we can replace it as F is equal to Fm into 1 minus EC by VDC by 2 whole square. So, why this introduction is brought? So, if EC varies sinusoidally, there is an EC variance area sinusoidally, during the Fm will vary, the frequency will vary around a Fm. So, EC can go both positive and negative. So, this switching frequency F will be modulated around a value, and the maximum value is Fm. Okay. So, let us write down, let EC is equal to, we know EC for sine triangle PWM, the maximum value of the sinusoid, E maximum, it's vary depending on the modulation index. So, modulation index for sine triangle PWM we said for a half bridge converter it can go from 0 to 1. So, let write EC is equal to M VDC by 2 into sin omega t. Now, substitute this one, we will get the frequency variation of F with respect to the back EMF EC. So, here what we found out, for a back EMF load, for a sinusoidally varying back EMF load, that means for a sinusoidally varying back EMF load, the switching frequency varies for a fixed delta I. Delta I is the hysteresis band. So, for a constant switching frequency, we have to vary delta I. So, now let us find out how F varies for a back EMF load EC. EC varies like with a modulation index of M into VDC by 2 sin omega t. So, from this one we can easily find out how the output switching frequency varies. Again, let us go back to our equation, that is F is equal to, let us go back to our equation, F is equal to Fm into 1 minus EC by VDC by 2 whole square. Now, EC is equal to m into VDC by 2 sin omega t. Okay. Let us substitute this one in this one. So, here f will be equal to Fm into 1 minus m square, that is a modulation index, sin square omega t. This is the frequency variation. Okay. See, sin square omega t we can again represent as 1 minus cos 2 omega t by 2. So, this can be represented as Fm into 1 minus m square by 2 plus m square by 2. So, now when we substitute the value of EC into this one, the final equation is like this. So, if you see here, the switching frequency f varies, sinusoidally varies around an average value here. So, f varies around an average value. So, let us find out for what is this average value, how it depends, and it depends on the modulation index. So, for variable speed operation, we have to design the hysteresis band either for the maximum switching frequency or the average switching frequency, you can decide. So, let us see how this switching frequency variation is it is varying 2 times the frequency with respect to the back EMF law. Let us study in the next class.